All right, so for the second video of today, linear elastoplastic material, the main equations are the stress and the back stress. The stress is linear for the elastic strains, so it's some linear fourth order tensor times the elastic strain, so this epsilon minus epsilon p, that's the elastic strains. And then the back stress, which is a function of some hardening parameter alpha, which is an internal variable. And then you have the flow conditions or yield criteria, which is a function of the stresses and the back stresses that has to be less than or equal to 0. Then in case that you go beyond that yield criteria, then you get plastic flow, and you can have associative plasticity where the plastic flow is directly given by the yield condition. So the direction of the plastic flow is directly given by the derivative of the yield condition with respect to the stress, and the hardening parameters are directly determined by the derivative of the yield condition with respect to the back stress. That's for the associative plasticity. For non-associative plasticity, then the plastic flow and the hardening parameters are just some functions, not necessarily given by the yield condition. So some function for the plastic flow and some function for the hardening. And the loading unloading conditions that you have basically for the plastic materials that you have to also satisfy. And this is some nonlinear system of equations. So these are the in general the definition of the stresses and the evolution of the plastic strains. Again, note that the stresses can be evaluated once you know the elastic part of the strains. You could evaluate the stresses, so that's okay. Now, how is this complicated? And this is linear, right? But how is this complicated when you add plasticity? Is same thing as before. We have some ODE that represents either for the associative plasticity or non-associative plasticity. Regardless, basically you get a rate equation for the plasticity. So typically what we'll have is, once we discretize this, what we will know is we have some value of the plastic strains from the previous time step, and then we will have a guess for the total strains for this time step. Based on this guess for the total strains, we can compute the updated plastic strains. Once we have updated the plastic strains, we can compute the stresses. And it's very similar to what I was explaining for viscoelasticity. The structure is more or less the same. So let's do, the first thing that you need to do is, like I was saying, you need to discretize. So upon discretization, typically what you have is you have solved everything for the previous time step. So you know everything that is with an n, that one you know because it's from the previous time step. So these ones are the ones that you're carrying from the previous time step, right? And then the unknowns are based on the, and so let me use a different one for, so this is your current guess for the total strains, and this comes from your global Newton iterations. So this is guess for current total strains, and this comes from the global Newton iterations. If you think of your global Newton Raphson iterations, you have loop over elements and then loop over integration points. At the integration points, based on the total displacements, you can compute these total strains, right? So this is your so computed from the guess for, so you choose like displacements for time n plus 1 iteration I of the Newton-Raphson. Of the global problem. So again, if you think back about the problem that you were doing for the homework 5, then you had a Newton-Raphson, right? Where at every iteration of the Newton-Raphson, you were computing some global displacements, evaluating the residual, evaluating the tangent, and then iterating until you got that displacement that satisfied, that led to a stress that satisfied the equilibrium, the static equilibrium. So here, same thing. You can imagine that the outer part of your code is the same. You have exactly the same Newton-Raphson as before. For each iteration, you are going to get some guess for the displacements. And now, based on that guess for the total displacements, for these iterations, you can compute the total strain. And the one thing that is different is that now you cannot evaluate the stress directly from this total strain, but instead you have to solve this system of equations for the new stress, the new back stress, the new plastic strain, right? So all of these are unknown. All of these are unknown. Again, unknown. So basically, you need to solve this system of equations. So here, so for, and in this case, it's going to be nonlinear. So this one you can solve with a local Newton-Raphson iteration. So you need to solve for your new variables. All of this. That's it. That's basically what you need to solve for with these equations. So this comes from the discretization, and this, by the way, this comes directly from the discretization of this and this and this. So hopefully that makes sense. Again, I want to repeat it many times so it's very clear. The outer part of your code is exactly the same as before. You have these global Newton-Raphson iterations where you are computing guesses for the strains. You're going to have your loop over elements, loop over integration points. For the integration points, based on your current displacements, you can compute the total strain. And the one thing that is different is that before, based on the current guess for the total strains, this green thing right here, you could compute directly the stress. That was it. You had the strain, compute the stress, and then with the stress, compute the residual and the tangent. Here, you don't have direct stresses, but instead you have to solve this system of equations which describes the plasticity. All right, so due to the inequality constraint, like this one right here, instead of solving this system, what is typically done is that you first assume that the plastic strains are frozen and you compute a trial value for the stress. You check if that satisfies the yield criterion. If it's inside of the yield criterion, then that's it, you're done. Then it's basically like a standard elastic step. And if not, then you do need to solve the equation. So it's like a predictor corrector scheme. So again, the way this is solved is there's several ways in which you can solve this. And the typical implementation is, okay, first assume that the plastic strains remain the same. So there's this trial here, right? This might not be the end solution, but for the first part is assume that the new plastic strain is the same as the before, and the new hardening variables are the same as the before time step. So do that. Based on that, you can compute the stress and the back stress for the new time step directly, right? Because that just means total strains which you have from your global displacements. This is basically the same as the previous time step. This is the same as the previous time step. So just multiply by these material constants, you get the new stress. Right? So you do that. But now these are called like trial, because this might not be true, right? But let's do that. If turns out that you satisfy the inequality in the yield function, so you are below yielding, that's it. Then you don't need to do anything else. That's it. So check flow rule. If you are less than or equal to 0, then it's an elastic step. So that's it. If it's an elastic, then you accept the trial, right? So the trial once becomes the actual one, and then the stress is the trial stress is the stress. So yeah, no problem right there. Like it's like some elastic step. But if this is greater than 0, that means that there's some plastic deformation. Then you actually do need to solve the equations. So you need to solve this system of equations. So these are 3 residuals. And again, you are solving for, let me mark this, sorry, this one is given. This one is the one that comes from your, what color was I using? I think I was using green. Yes. So again, this one right here comes from before, from your global Newton iterations. This one's right here, this one is from your previous time step, so you have that one. This one from your previous time step, so you have that one. And the unknowns are the new stress, the new back stress, the flow, the plastic flow, and that's it. So those are the 3 things that you need to solve for. The new the new stress, the new back stress, and the actual plastic flow. Yeah, so that's it. How do you solve this system of equations? Well, with Newton-Raphson. So again, just to remind you, this is the system of equations. How do you solve this? Newton-Raphson, local Newton-Raphson. Note that this is another system of equations, another Newton-Raphson. So you have the global Newton-Raphson, which is trying to solve for the global displacements, the displacements of all the nodes. And now this Newton-Raphson is at the integration point. So at the integration point, like I said, you come in with the previous time step values, and you come in with your current guess of the total strains. And then your goal is to find the new stresses, the plastic flow, and the new back stresses. And to do that, you need to solve these equations, but they are nonlinear. So Newton-Raphson, but only at this integration point. And the tangent for that local Newton-Raphson is this. So you iterate in the local, at the integration point, you do some iterations, and then ideally you solve these equations, this system of equations, and that gives you the new values for the stresses and the plastic flow and the back stress. And that's about it. So once you solve this system of equations, then you get your stresses. With your stresses, you can compute your residual. So let me do same as before. Again, here you have, I'll just copy what I had sketched out before, because it's exactly the same. It's just, the idea is the same. It's just that the system that you need to solve is a little bit different. But let me paste that here. So here you're going to initialize your internal variables. So now you initialize your hardening parameters. You can initialize your back stress. You can initialize your plastic deformation. You can initialize your stress. So basically you initialize all the internal variables. Then you're going to loop over time step. For the time steps, you have iterations, global iterations. So you start for the iteration 0, your initial guess for the displacements. Then you're going to have a Newton-Raphson for the global problem, where you are trying to solve for these displacements of the nodes. How do you do that? You are going to assemble the residuals. So loop over elements, loop over integration points. Based on the current iteration, the displacements that you have for the current iteration, which are these u n plus 1 I, you can compute the total strain. In this case, no deviatoric strain, just total strain from this iteration. So this is same as before. Up to this point, looks the same as before. Total strain based on current guess for total displacements. Right? But now, here, this is the only thing that is different. Local problem solving for plasticity. Solve plasticity. So what you're going to do after this solve the plasticity is actually this one. In this case, it's all in the before case. I could do it separately, but here it's just all together. So compute update for new back stress, right? The new stress, the new plastic strains. So basically solve the plasticity problem, right? Based on the current value of the total strains and the previous value of the, here you also need, I should also say that this typically also depends on current iteration and also based also on the previous values, on previous time step values for the plastic strain and the stress and the back stress at n. So all the things that you have from the previous time step and the new total strains, you solve the plasticity problem, which gives you the new values for the. So all of these are sort of all your plasticity requirements, like back stress, hardening, plastic flow, plastic strains, new stresses that satisfy this plasticity problem. And then once you do that, then you can assemble your residual with these stresses that you solved from this plasticity problem locally. And then you need to compute the tangent. And similarly to before, the tangent is, the geometric part is the same, and you have to be careful with the other part, the material part, because you have one part which is the same as before, which is you want to take the derivative when there's no plasticity. So this one is ignoring plasticity. And then you have to do what is the change in stress because of plastic flow. So this is a little bit trickier. So you can, depends on what you choose as your internal variables, but you can choose this. It actually, you have to do all of them. You have to do, this requires some of all the things that are depending on the plastic part. So if your stress is a function of the q's, then you would also need, derivative of sigma with respect to q with respect to the strain. So it really depends on what your function of the stress looks like. So if your new stress is a function of all the other variables, all the other orange variables, then this one would actually have not just the derivative with respect to the epsilon p, but you would have derivative with respect to the alpha, and then alpha with respect to the increment in the strains, and so on. And that's it. So hopefully this structure makes sense. In the book, they give the part for this second part of the tangent. So this one which is the sum of everything that depends on the plastic. So this is everything related to change in stress due to plastic deformation. And so this depends on the equations that you are solving for the plasticity problem. And let's call this dpm plus 1. And so that one is actually, this depends on the algorithm that you're using for solving. So this really depends on how you are setting up your plasticity problem. Not only what the equations are, but how you are solving them. Because this entails, like, for example, implicit Euler or forward Euler would give you a different tangent, because this is really depending on how you are updating them. For this particular case that I was describing, the tangent is given by for the local. This is the tangent for the local Newton-Raphson, and so it turns out. So you can see here the tangent for the local Newton-Raphson is the entire thing, and it turns out that the first equation is the equation related to the change of stress. So this is the residual for the stress equation, right? Which is the one that is used to get the new stress. And so here, this is the first entry in that local Newton-Raphson tangent. If you take the first entry, that is the one that you need for the global tangent. And again, this is just because of the way we are solving the plasticity problem. So it all depends on how you're solving the plasticity problem. You want to compute what is the derivative of the stresses with respect to the plastic strains, and then that with respect to the total strains. Yeah. So for this case, it's just the first entry of that local Newton-Raphson tangent. For J2 plasticity, where you have the associative flow rule, the equations that describe this are, again, some linear decomposition of the strains, the deviatoric strains into an elastic part and a plastic part, a deviatoric stress which depends on the elastic deviatoric strains, and a pressure, a hydrostatic stress which depends on the trace of the total elastic strains, not just the deviatoric part. And a yield condition, right, which depends on the stress, the deviatoric stress, and the back stress, and these hardening parameters. So the associative flow rules from the yield condition give you rate of change of the plastic deformation, rate of change of the back stress, rate of change of the hardening parameters, by just taking partial derivatives with respect to the corresponding variables. I don't know if this is correct. I'm gonna guess it is, but I'm not sure. Again, these are the equations, but you need to discretize them. So once you discretize them, then you're gonna get that the new plastic strain is, this one is known as before. So these ones are known. You have those from the previous time step. And then the unknown things are the new plastic strain, the new back stress, the new hardening, and the plastic flow. So those are the things that are unknown, right? And that you need to solve for. And once you have updated for the new plastic strains, back stress, hardening parameters, you can evaluate your new stress. So this is technically also unknown, right? So this is also unknown. Once you have solved for the updated of the plastic strains, you can compute your updated stress. And the thing is, there seems to be only 3 equations here and one unknown, which is the plastic flow. And the thing with the plastic flow is that it's an inequality constraint. So that one could be 0 or could be non-zero, depending on the inequality constraint. And so here you have to do the same thing as I said before, trial and then a correction. So what you do is, again, like a predictor corrector algorithm. So again, you are in your Newton-Raphson loop, you are looping over elements, looping over integration points. You have your values for the plastic strain and the back stress and the hardening from the previous time step. And the first thing that you're gonna do is assume that that is the same for the current time step. So assume that there is no change in the plasticity, right? So the trials here is basically assume that the new plastic strain is the same. Let me just say trial is the same as the previous one. Assume that the new Q at n+1 is the same as the Qn. Assume that the alpha n+1 is the same as the alpha n. So that's your first assumption, is that there's no plastic deformation. And so if there's no plastic deformation, you can compute the corresponding stresses, right? So that's what you do, and that's your trial. And then there's two possibilities. One possibility is that this trial is inside of the yield surface. So this Fn equals 0, that's the yield surface. And let's assume that your trial lands over here. So in your yield space, you are still inside. In that case, it's an elastic step, so you take the trials, right? Or it could happen that when you evaluate this trial stress, that you are actually outside of your initial yield surface. So this was your initial yield surface, this was your initial point, and then based on your current, and this is what comes from the global Newton-Raphson, right? So this is from the global Newton-Raphson, this green one. Based on that green one, and keeping the plastic variables fixed, you evaluate your trial stress, and I'm outside of this yield surface. So then you need to update the yield surface. So that's why here you have the new yield surface. You need your new yield surface, and you need your stress, which should be on that surface. And so that's what we need to do. And the way it's done is you have to project this back here. Some simple things when you have this associative plasticity is that the direction of the plastic flow is directly given by the trial. So this is why this is called the radial return mapping, because your actual final stress is basically projected back to the yield surface based on the trial. So once you compute the trial, that one actually defines your direction of plastic flow. And so that is known, and then the only thing that you need to determine is how much basically how much are you going to have plastic flow, which basically determines how much this changes, this yield surface moves. So how do you do that? Well, you only need to solve for basically the equation for the new yield surface, which depends only on the new plastic flow. So your unknown here is only this. So for this might be nonlinear, so you might need to use Newton-Raphson here, but it's a nonlinear equation with a single variable. So you solve for that plastic flow for the new time step. And if hardening is linear, so there's no this h right here, this might be some nonlinear function, but if it's a linear function, so if it's just a parameter times the alpha from before, then you can actually, you don't even need to do a Newton-Raphson locally. Then you can directly solve for this plastic flow. No need to do Newton-Raphson iterations. So yeah, this one's a lot simpler. So again, you start with your current guess. From this comes from your global Newton-Raphson iterations. You have a guess for the total strains. Based on that, assuming that the plastic terms don't change, compute these trial stresses, see if you are inside of the yield surface, then that's it. You take the trial because there's no plasticity. You don't need to update any of the plastic stuff. And then if not, then you need to project that your stress trial, you need to project that back to your new yield surface. And the direction of plastic flow is given actually by that trial. So that gives you already your direction of plastic flow. And how much you flow, you need to solve an equation, which is basically the equation for the yield surface. And then if it's hardening is linear, then you can actually solve it without Newton-Raphson locally. So just directly solve for that plastic flow. And that's it. So now you know your plastic flow, and then you can compute your new stress, right? And that's it. That's all you needed to do. Tangent is also needed. Again, the tangent is, like I was saying before, you have the elastic part of the tangent. Obviously, in the tangent, you have the geometric part. That always stays the same. And then you have the material part. And then in the material part, then you have the elastic part. So this would be ignoring the plasticity, just the derivative of the stresses with respect to the total strains in your constitutive equation. So that like explicit derivative of this with respect to this epsilon n plus 1. So the explicit derivative with respect to the global strains. And then plus you need the derivatives with respect to the plasticity terms. So in this case, the stress depends on both it depends on the plastic strain, right? So if you remember the stress, it's right here. It basically, here, you can see that the stress depends on the total strains. So this is the elastic part. So these are the total elastic strains, and these are the previous elastic strains. You see that if plasticity is fixed, so this one uses the previous time step. And then this is the correction if there is plastic flow, right? And so the tangent now needs the derivative of this with respect to the epsilon n plus 1. This is almost epsilon n plus 1. This is just that minus the trace of epsilon n plus 1. So this is just the deviatoric part. So the derivative of this with respect to epsilon n plus 1. And then now these are the plastic terms. And so they also depend on the total strains. So by the chain rule, you need to take derivative of this, of the stress with respect to the plastic flow times derivative of the plastic flow with respect to the strains, and the derivative of this with respect to the direction of the plastic flow, and then times the derivative of this with respect to the total strains. So that is why you have these two extra terms here. So this is basically derivative of the stress at n plus 1 with respect to the plastic flow times the derivative of the plastic flow with respect to the total strains. And this one right here is derivative of the stress with respect to the direction of plastic flow. And then this direction of plastic flow depends on the strains. This dependence is given by your algorithm again. So this depends on how you are evaluating the plastic problem. In the particular case that we were discussing, these are the formulas. You have to be a little bit careful with that one, because that one, yeah, I think you need to wrap your head around that one a little bit, because that one is basically coming from, you can see like n plus 1 depends on this S trial, and this S trial you need to sort of backtrack where this is coming from, right? So to see that it actually depends on these total strains. So this nn plus 1 depends on this trial of the stress. And then if you go back here, you can see that this S trial actually depends on the total strains. So that's how you would get back. You need to take a derivative of this with respect to the total strains. And that's basically this term right here. So you can see that there's derivative of the direction of the plastic flow with respect to the total strains is chain rule. So the derivative of this with respect to the Sn plus 1. And then this one, yeah, I mean, this is given by, where are you? By this guy right here. So 2 mu and then derivative of the deviatoric strains with respect to the total strains. So that's actually how this, yeah, that's how this comes about. And then, well, I ignore you also need to worry about this denominator, but yeah, I would have to do it more carefully. But does that make sense? Hopefully that makes sense. That's it. That's all I have.